All right, welcome to one of the more annoying types of problems. They're very difficult to execute, and I personally, it seems like I make a lot of mistakes on these, just little errors, The algebraic errors really add up on these because we're going to both be taking limits and integrals at the same time, so it's just really hard to keep all the stuff straight, end up plugging in multiple times, so it's like, you're just a pain anyway. These are a very mathy problem, and here's what's going on. Notice how we have a limit, upper limit of infinity, or an upper bound of the integrals infinity. That's not cool. And the reason it's not cool is because mathematicians don't like the little symbol infinity. You tell a mathematician infinity, what they're going to say is, oh, you mean a number that's increasing without bound? So the problem is infinity is not a specific number. It's just the concept of a ridiculously big and increasing forever type number. It's almost like an asymptote. So the problem is that since this little infinity is sort of the idea of a number, but it's really more a mathematical concept than a number, that means you can't actually technically plug it into anything. So if you want to integrate from 1 to infinity, you can't really do that. What you can do though, and this is where the mathematic trickiness comes in, and the limits, is you could replace that upper infinity thing with a letter, and then say, hey, let's take the limit as that letter goes to infinity. So it's sort of a mathy dodge they've done to use a limit to sort of make an integral problem that wasn't legal. But of course, how do you find limits when b is approaching infinity? You just try plugging in infinity, right? So that's what's dumb about these, is that even though you put this limit problem in front of it and stuff, ultimately the same result happens, which is you're going to ultimately plug in infinity and see if the thing exists or not, which is the same thing you always did limit problems before. So this is really a cheesy dodge. It's silly, leads to a lot of extra busy work, but at the same time, you won't get full credit unless you do this limit thing. Because really the whole point of a question like this, where you throw in infinity as one of the limits, really all they're testing is your ability to get really mathy for a second and sort of think as a mathematician. So I know I'm using a lot of quotes, but that's because I really hate this type of problem because it's a bunch of mathematical junk. You know, even as someone who really likes science and physics and stuff, I don't see the point of this. So that's a pretty high bar to clear, where even I think it's a really stupid thing to be wasting everyone's time with. But hey, that's where you're at. So I'm gonna do 4 examples. I'm gonna try and get through these without making any dumb mistakes. If you see any dissolves in here, that's because I screwed up and I had to retry the problem. So we'll see if I make it. All right, so what's the first step? We got to rewrite this as a limit problem. So all we're going to do is replace that upper limit, we're going to replace with the letter b, just because, why am I using b? Doesn't matter at all. It's just that normally when you do a definite integral, they always sort of do a and b as the limits of integration, or you'll see the, a and b are just sort of like the default numbers or letters you always use for an interval, like the interval notation. So just figure we'll put a b up there. The bottom number is fine, so you'll just leave that as a 1. And now this b is what we're going to take the limit as b approaches infinity. All right, so let's see what happens. And that's, of course, the limit, or the integral of 1 over x squared. Which, you know what, we might as well just write as x to the minus 2 right now, so it saves us chances to screw up, which I'm badly in need of. All right, so x to the minus 2, integral of that would be x to the minus 1 over negative 1, but of course that's a limit as b approaches infinity, and then we're going from 1 to b. Kind of a pain, right? We have to keep rewriting this silly limit notation. All right, so we got limit as b approaches infinity. Now x to the minus 1 is just 1 over x, and of course negative 1 is just negative 1, so that's negative 1 over x from 1 to b. All right, so step number 1, what we're going to do is we're going to plug in b, do our sort of plug in b as our limit of integration and work out the definite integral first, then we'll take the limit. So we're still going to have this limit as b approaches infinity thing going on until the last second. So I got negative 1 over the top limit, which is b, minus, now I got to plug in my lower limit, so negative 1 over 1. Those cancel. So I just get negative 1 over b plus 1. And of course this is still, don't need to evaluate that anymore because I plugged in my b's already. All right, so at this point we just have a straight up limit problem. So what is the limit as b approaches infinity of 1 over b? So it's basically negative 1 over infinity. Negative 1 over a huge number is 0. So that first term is just 0. And if you're not familiar with limits or you've totally forgotten them, definitely go back and check out. There's a bunch of good limits videos on this website in the calculus section. And then plus 1. So that equals 1. Yay, that's the number I was supposed to get. So I think we just got through one in one piece. Congratulations to me. So all right, so I think you're getting the hang of this already, but let's do 3 more just in case. Now the last problem I'm going to do is one that's a little bit trickier, where we'll have some funky limits of integration. So, and also sometimes you'll have to switch limits, which we'll get to in a second. So once again, we got an infinity up here, which is what makes this a bummer problem. So limit as, got to come up with a letter first, so from 1 to b, as b approaches infinity. And I'll just rewrite this integral as 3, and then that's really a cube root of x downstairs is x to the negative 1/3 dx. Okay, so now I'm ready to integrate. Still going to limit as b approaches infinity. And you got 3, integral of x to the negative 1/3 is x to the 2/3 over 2/3. Right. So that's a limit as b approaches infinity. Oops, this needs to be evaluated from 1 to b. So many things to remember in these problems, it's ridiculous. Alright, so we got to plug in 3. And then dividing by 2/3 is really the same as multiplying by 3/2. So we've got 3, and then we've got that 2/3 downstairs becomes a 3/2 upstairs. Then we got x to 2/3 still being evaluated from 1 to b. So 3 times 3/2 is 9/2. Oh man, I forgot my limit. I don't like these problems. Limit from b to infinity of 9/2 times x to 2/3 evaluated from 1 to b. You really want to break this out in a bunch of steps because it's so easy to make a mistake. You just don't want to do anything in your head or you'll get these wrong. So we got 9/2. And now I'm going to plug in my limits of integration finally. So I got b to the 2/3. Don't need that final. Minus, and then just 1 to the 2/3 is 1. All right, so what is the limit as b approaches infinity of b to the 2/3? Infinity to the 2/3 is infinity. And minus 1. So here's the problem. We've got an infinity in our answer, and it's not downstairs, it's upstairs. It's just a regular number, which means this diverges. So the limit, back when you're doing limits, you might have said limit does not exist or whatever. But for this type of problem, if the limit, if you don't get a whole number, like if you don't get 5 or some finite number, if your answer is sort of infinity related, you say this diverges. So don't really need to know why it's called diverges. That's just a mathy way to do it. And obviously these problems are very mathy. That's why we're doing them in the first place. So you just write down diverges for anything where the limit does not exist or is, a really big increasing number without bound kind of thing. All right, so here's a funky one. We've got infinity both as the lower bound and the upper bound. So kind of a bummer. This one, of course, is negative infinity. But nonetheless, we've got basically 2 improper integrals in one. So we're going to take advantage of an integral property, which is that if you're integrating anything from a to b, we can turn that into integral from a to a random number like 1, or sometimes they'll call it c, and then add to that the integral from that same number c to b. And the concept here is just that when you do a definite integral, you're finding the area under a curve, right? So if you're going from a to b, you're finding this whole area. And the theory was that, hey, if you want to find that whole area, instead of taking it all in one swipe, you could sort of throw a random number c in there, and then you can take the integral from a to c would just be this first chunk of area, and then c to b would just be that second chunk of area, and obviously those 2 chunks of area add up to the same thing as the original, right? You just kind of took this overall chunk and broke it up into 2 smaller pieces of area, and that's all we're going to do now to get so that we only have to deal with 1 infinity per integral. So I'm just going to randomly throw 0. When in doubt, use 0 for stuff. So I'm just going to take this integral from negative infinity to infinity and turn that into an integral from 0 to infinity plus an integral, negative infinity to 0. Probably consider that the first one would be negative infinity to 0, and then we'll add the integral from 0 to infinity. So by breaking up into 2 improper integrals, each of these is improper in its own right because each of these has an infinity in it. But the cool thing here is that we've got just 2 basic improper integrals that we can deal with separately. So we can use the same technique we used in the last one. All right, so this is going to be, now we'll need to have a different a and b situation. So we'll take the limit, just call it a approaching infinity, because it's a lower limit. So replace negative infinity with an a, if that's a negative infinity. But then of course, now that limit as a approaches negative infinity to 0 of 2 over 4 plus x squared plus the integral from 0 to b. Oops. I'm telling you, man, these problems are rough. Limit as b approaches positive infinity times the integral from 0 to b of 2 over 4 plus x squared. Now at this point you might be noticing, man, what the heck does 4 plus x squared downstairs integrate to? That's nuts. Well, let's take it separately. The integral, this, if you're looking at this maybe to be a natural log or something like 1 over u, doesn't work because if you make the whole denominator equal to u, then your du would have an x in it, but we don't have an x upstairs to mess with. So it turns out what's going on is this is an arctangent, which is annoying. So this is going to be the arctangent. Our a is 4, so let's break out this integral separately. The integral of 2 dx over 4 plus x squared. Our u in an arctangent, our u is whatever's getting squared, so in this case u just equals x, which means our du is just dx, so that's great. And then our a, which is just the number here, this number is a squared in the arctangent formula, so a equals 2. It's the square root of that constant downstairs. It's being added x squared. So this 2 upstairs is actually extraneous. We don't need it. So the integral of this is just going to be 2 times 1 over a, so 1 over 2, tan minus 1 of u, which is x, over 2. And of course these cancel, so we just end up with arctangent of x over 2 as our integral. So that's what's going to happen when I integral this. I'm just going to get the same thing. So I'm going to get limit as a approaches negative infinity of tan minus 1 x over 2. So remember these 2's canceled here, so that's why there's nothing but inverse tangent. And of course that is from 0 to a. And then to that I have to add the limit as b approaches positive infinity of the same integral. Because remember, even though we've broken into 2 integrals, they're of the same thing, 2 over 4x plus x squared. So that means we get the same integral, so negative 1 of x over 2, evaluated from 0 to b. Oh man, this one should have been a to 0. All right, you can see how tedious these are. This is kind of crazy. So this first one, now I'm going to plug in the limits of integration. So I'm going to get tan minus 1 of 0 over 2 minus tan minus 1 of a over 2. This is still the limit as a approaches negative infinity. Then I got to take the limit as b approaches positive infinity of plug in b minus tan minus 1 of 0. All right. Horrible mess, but hopefully it's going to work out. So these first 2 are with my a approaching infinity, negative infinity. So what is the inverse tangent of 0? That's just 0. And I'm subtracting the inverse tangent of limit as a approaches negative infinity, so negative infinity. So tan minus 1 or inverse tangent of negative infinity. Now it's technically negative infinity over 2, but then again, negative infinity and negative infinity over 2 both the same thing. They're a giant negative number. All right, so then I've got the limit as b approaches infinity of inverse tangent of b over 2. And again, infinity over 2, pretty much just infinity. Minus tan of 0, which is 0. All right, so you with me so far? This is kind of crazy, but what's going on is I've got some negative infinities. Now you might be thinking, hey Chris, infinity is undefined, or at least, how infinity usually makes limits not exist. The thing is, this is an inverse tangent. We're not taking the tangent of infinity, which, who knows? We're taking the inverse tangent of infinity, which means we're looking for an angle whose tangent is essentially undefined and negative. But guess what? Tangent, if you think about the graph of tangent, it does that crazy thing, kind of like disco shape, like this. And it's actually, there's a x over 2, a couple of asymptotes, and it kind of does this through 0. So it turns out that right here, at negative pi over 2, we've got an inverse tangent of negative infinity, or we've got a tangent of negative infinity, which means that inverse tangent of negative infinity is actually negative pi over 2. Because at negative pi over 2, the tangent's negative infinity. And then, well, technically it doesn't exist for negative pi over 2, but right next to that, the limit is theta approaches negative infinity, is negative pi over 2, and then we have a negative out in front of it, right here. So these end up canceling out, we just get pi over 2. And then inverse tangent of infinity, same story except it's positive, because that's going up here. So as if you take, like think about what the tangent of pi over 2 would be, the tangent of 90 degrees. It's undefined because cosine is 0 and that's downstairs, but it's positively undefined. So the limit is actually pi over 2. And crazily enough, pi over 2 plus pi over 2 is just pi. So out of all that wacky goodness, we get down to just pi. Kind of strange, pretty exciting stuff. Now this doesn't come up a lot. These limit problems with inverse, trig functions and stuff does not come up a lot, and that's why I haven't seen it before. But on the same token, you really don't have to worry about this unless you're in a very hard AP class. All right, last one. Let's take a look. So that once again, we're back to just regular old infinity upstairs and a number downstairs, which is actually kind of a relief, right? That's why I put these in reverse order. Normally I'd put the hardest problem last, but I wanted to throw a not quite as hard problem last to show you that, hey, you know what? Once you've seen the bad ones, the easy ones, or the not as hard ones, are not nearly as scary. So now, since we only have one limit, we're just going to take limit as, call that b, approaches positive infinity, of the integral from 0 to b of cosine pi x dx. Now the one subtlety on this one is that we do have a u sub situation because it's the cosine not just of x but of pi x. So that means we have to do u sub. So u equals pi x, and therefore du just equals pi dx. So that means I need a pi right here in front of the dx, which means I have to put a 1 over pi out front to compensate, because you can't just go around willy-nilly sticking a pi in anywhere unless you put in a 1 over pi to make up for it. All right, so at this point we got the limit as b approaches infinity of the integral of 1 over pi times the integral from 0 to b of cosine of u du, which is really just, at this point, I'm just writing out a step we could have done in our heads, but this integrates to the limit as b approaches infinity. Integral of cosine of x is sine x. So sine of pi x, really it's the sine of u, but then we're going to stick it back in, so we get the sine of pi x as we go from 0 to b. Alright, so this is going to be the limit as b approaches infinity. Now we just plug in our limits of integration. So it'll be sine of pi times b minus the sine of 0 times b. I'm sorry, 0 pi. Alright, is this looking pretty good so far? Let's see what happens. Now the sine of 0 is just 0, so that's pretty good. What is the limit as b approaches infinity of sine pi b? It turns out there is no limit for this one. It's kind of a special case because as theta gets bigger and bigger, doesn't sine just pretty much wiggle back and forth forever? It just keeps going back and forth, right? So as you go to infinity, it just never stops going back and forth. If this thing had sort of like wiggled back and forth but gotten smaller and smaller and got really flat or something, then it might have a limit. But this is a special case of limits where a function's going back and forth. You really can't pin it down. It's somewhere between -1 and 1, but it just depends on exactly what infinity is. Is infinity here, or if you just add a pi over 2, all of a sudden everything's flipped over. So this diverges, or there is no limit, is another way of writing it, because the thing goes back and forth, so you can't just point to a single number of like yeah, sine approaches -1, or sine approaches +1, or 0 or something. As we approach infinity, it just keeps going back and forth between -1 and 1 forever, and therefore we cannot pin it down. Can't write down a number. When you can't write down a number for our limit, it's no limit, and therefore the integral diverges. So it's just that little subtlety of where when a limit doesn't exist, when you take the limit on one of these integral problems, you just say that diverges, meaning the area is either infinite or you can't pin it down and say what the area is. So that's it for these ones where you have infinity as a limit of integration. The other type of improper integral, what we'll cover in the next video, is the ones where it actually doesn't look like there's anything wrong with the integral. It's just if you really look at it closely, you'll realize that the function doesn't exist, either at the upper or lower bound. So we'll learn how to do that one in the next video, but I guarantee you, and you can probably guess, it's going to involve a limit problem. So stick around for that.